Let's talk a little bit more about epoxide ring opening. So we saw this previously, how a good nucleophile like methoxide can open up an epoxide ring under a typical SN2 reaction. So here, again, I've got a great nucleophile, backside attack on the less hindered side, right? Because here, this is too crowded for my nucleophile to get in to do the backside attack it needs to do. So we have backside attack here. Again, an SN2 reaction gives us a stereo-controlled reaction. We actually call this stereo-specific because I'm always going to get backside attack. So now I want to talk about acid-catalyzed epoxide ring opening. Okay, so before we were counting on a really good nucleophile, but when I have an acid catalyst, I'm not really making a really good nucleophile, I'm making a really good electrophile. Okay? So if I just have an epoxide and methanol together, neither one of these is very reactive. They're just going to stare at each other. Right? Up here, I had to make the methanol more reactive, but down here, a catalytic acid, whether it's sulfuric acid or hydrochloric acid or any kind of strong acid, my acid is going to protonate the oxygen here to give me something that looks like this. Okay. Again, acid catalysts make electrophiles more electrophilic. Here the reaction goes because I have a really hot nucleophile. Here the reaction goes because I have a really hot electrophile here. This isn't the first time that we've seen a three-membered ring with a positive charge. We just saw this when it came to halogenation. Right? If I attack an alkene with either bromine or chlorine, Cl2Br2, we end up with these bromonium ions. And we said that the selectivity here is kind of weird. We called it a loose SN2 because here we would attack the more hindered side like an SN1, but we'd get fully trans products because we'd still have backside attack. So it's not quite the same mechanism as up here. The selectivity is different. And it's actually the same for this. So both three-membered rings, both positive charge. In both cases, my weak nucleophile, which in this case is still methanol, is going to attack the more substituted end because that's where the positive charge is. So just like when we had bromine and water, for instance, my weak nucleophile will attack the more substituted end because that's where the more positive charge is building up. And like that, we're going to see stereo control, so it's coming from the backside. We'll see inversion at that center here, and then the OH is down there. So again, notice I have different products, whether I do this under basic or under acidic conditions. To take a quick detour, there are lots of organic reactions that use this three-membered ring with a positive charge kind of structure, and they all more or less react the same, with some nucleophile attacking at the more substituted end. So we've seen Cl and Br, bromonium ions. Now we've seen protonated epoxides. We can also see this with mercury and selenium. And I want to go through mercury very quickly here, not because I'm going to test you on it, I am not, but because if you take the MCAT, people who write the MCAT still think that chemists use mercury every day. We do not. But it works the same way. So some alkene reacts with a mercury 2 salt to get an intermediate like bromine, three-membered ring. Water then attacks there. Your intermediate then has a new carbon-oxygen bond here. It's an alcohol. Your mercury goes over there. That mercury is taken care of by some reducing agent, just replaced with a hydrogen. And this is essentially another way to go from an alkene to the Markovnikov alcohol if you don't want to use strong acid. So again, we won't really see this on homework or tests, but if you run across it in studying for MCAT or PCAT stuff, this is how oxymercuration works. Okay, let's combine two of the things we've talked about this week. Let's combine acid-catalyzed epoxide opening with thinking about alkenes as nucleophiles. Okay, here's the situation. This is squalene. Squalene is a terpenoid. We'll learn about it at the end of the class. Notably, it is not chiral at all. It is also the starting material for pretty much every steroid there is, going through lanosterol. Check out all the stereocenters in lanosterol. Lots of them, right? There. Lots of stereochemistry. No stereochemistry in squalene. So how do we get from something achiral to something chiral like this? Well, it goes through the epoxide. So squalene epoxidase does just what it sounds like it does. It specifically puts the epoxide group right there. And now these arrows are telling us that this is getting protonated by some enzyme. And when it does, that epoxide is now a really good electrophile. What's the nucleophile? The nucleophile is going to be the double bonds within the molecule. So this pi bond can go act like a nucleophile to go make a new bond there. And when it does that, that makes this carbon electron pour. And so the pi bond over here can go make a bond like that, which makes this carbon electron pour, and it keeps zipping up like so. So we have all these new sigma bonds that more or less get made at the same time. Now this second step is kind of convoluted. It's essentially a bunch of the hydride and methyl shifts that we talked about as rearrangement products for carbocation reactions. We call them hydride and methyl shifts. The technical term is Wagner-Meerwein. But that's not the focus here. The focus here is that I got from something achiral to something very chiral. And I made a bunch of new carbon-carbon sigma bonds by having my alkenes act as nucleophiles, my pi bonds act as nucleophiles, and my protonated epoxide act as an electrophile. So obviously lots of enzymes are involved with this, but it was a hypothesis back in the 60s called the Stork-Eschenmoser hypothesis that we didn't actually need an enzyme to make all these stereocenters, right? So the idea here is that this isn't just a coin flip for each of, let's say, the 6 contiguous stereocenters in progesterone. The hypothesis is that a polyene like squalene is kind of set up to give you this diastereomer specifically, just because of the way the polyene lies. So the Stork-Eschenmoser hypothesis is that even an achiral polyene like squalene can yield these complex chiral steroids pretty diastereo selectively. So this hypothesis was tested in 1971 by Bill Summer Johnson. So Johnson took several steps to get to this alcohol, and then he treated it, or his group treated it with an acid catalyst and this cation trap. So the acid catalyst is going to do what acid does. It's going to protonate this oxygen here. This is going to act as a leaving group, and that's going to give us this cation. And notice that all the trans double bonds in the system kind of lend it to start to coil up like this. And so you can see how my arrows are going to go, right? So this is kind of already delocalized there. But this pi bond, it can swing over to fill that gap. That leaves this positive charge here. So this pi bond can go swing down, and one of these pi bonds can swing down. And then it's trapped by this cation trap like that. And then we get this intermediate. So notice a bunch of new carbon-carbon bonds. New carbon-carbon bond here, a new one here, and a new one there. And stereoselectively, all of these bridgehead carbons are set because we want the nice chair conformation. And then once we get that cation, when we treat it with aqueous base, we end up essentially methoxide attacks this whole thing falls apart, and we get to this. So we can talk about this mechanism later on. But the idea is that, again, mostly achiral polyene can get to a profoundly chiral compound. And it works by using alkenes to trap cations. So this cation is made from an alcohol, but we can also get something like a cation from this epoxide. So protonated epoxides, good electrophiles, can get attacked by weak nucleophiles. This is an early example of what's called a biomimetic synthesis. So here, Johnson is specifically taking inspiration from how nature was thought to zip these polycyclic compounds together from linear polyenes like squalene. So he's trying to copy nature in how he did it. In this case, he was able to find success.